You can see full screen, right?
Yes, we can see.
Okay.
So thank you, sir. I think we can start. So our next speaker is Dr. Amit Prashant, who will present on high performance reinforced soil structures and for critical infrastructures application in high speed railway rails. So Dr. Prashant is the BIA Standardization Chair Professor and Dean of R&D at IIT Gandhinagar. He completed his BE from IIT Roorkee in 1997 and PhD from University of Tennessee in 2004. He worked as assistant professor at IIT Kanpur from 2005 to 2010 before joining IIT Gandhinagar. His research focused on constitute modeling of soil, earthquake, geotechnical engineering, and geosynthetics, involving both experimental and numerical approaches. Please welcome Dr. Prashant.
Thank you, Sumit. Uh, I hope you all had a productive day. And this talk is mainly going to be about GRS structures with high performance requirements, especially applicable to high speed railway. So, a little bit of background about geosynthetic reinforced soil walls. We all know probably, or most of us will know probably what the GRS walls are, but yet to revise the, you can say, the components that are involved. There are reinforcements that are going into select fills in general, and select fill means granular soils freely draining, and that is rain. You can say self-sufficient in terms of controlling the deformations that can happen with vertical uh, raising of soil. But on the fascia, we have local support provided as well as aesthetics point of view, and that is connected with some kind of arrangement at certain intervals, while the fill is made in lifts of about 300 to 600, depending on what kind of a spacing you want to provide to reinforcement. And the lift is compacted in layers of 200 or 150, 200 in that range. The fascia is rested on a leveling pad, which is not a foundation, it's just leveling pad in some sense. You can say the reinforcement zone itself needs a foundation. So overall, the length of the reinforcement below that, the soil has to be prepared for foundation as such. Uh, Basic principles of analysis are similar to what you would do for retaining structures in Coulomb's method or for slopes in many times. So, but yet there is, of course, there is some difference with the assumed wedge that is based on experience. Uh, what is expected to be a failure slip in the back of the wall, and reinforcements come as providing tensile resistance in addition to the resistance that is provided by slip by soil being frictional material. If I compare different types of structures, uh, the cost of GRS walls is much lower. And if you look at many of the flyovers that are being made, highways have taken over most of the projects, uh, taken over this GRS technology very well, and use that in many projects nowadays. And that has reduced cost for those stretches to almost half. So you can say almost like in the cost of one flyover that used to be about 25 years back. If I compare that, it can be done in almost 50-60% cost now. And that the same advantage, the cost advantage, is available for any structure that you make using GRS walls in any sector. And now it is this whole technology is percolating into railways, not only for the side slopes, but also providing the support to the tracks on embankments. So those embankments where tracks are being made, slowly you will probably see in near future that we have GRS wall being used. Construction technique, of course, very simple, that you prepare the ground, you lay the geogrid or similar kind of products, which provide uniaxial direction of reinforcement. And then you lay some kind of blocks or some kind of fascia, and then fill the soil, compact the soil, first filling some 200 or so, and then putting roller on top. So we never put roller directly on the reinforcement, and compact the soil well before going to the next level where reinforcement is to be laid. And we continue this exercise step by step. There are many examples of applications. Of course, highways you have seen, railways is internationally being made. In India also, it is coming up now. And second application is, of course, on the side is through abutments. So instead of providing the retaining wall type or concrete abutments, we can provide geosynthetic reinforced walls. So design is slightly different. Of course, deformations are supposed to be less in true abutments, but one of the biggest advantage of true abutments with this is that the deformations of uh, the back approach and the true abutment are similar. So this bump in the curve is generally not a problem with reinforced true abutments. But there are other applications of hill protection, etc. And also now we are going to see some waterfront structures in canals and rivers. We are working on some projects, and they will become available for, you can say, to see in next couple of years. So that is another sector opening for GRS walls and slopes. Now, so evolution in terms of how this whole technology has evolved. Some simple retaining structures we started with, and then it found a grip in highways mainly for approach road. And then on top of that, there were some, of course, when you have some landscape which is not really uniform, then we have used many places now GRS walls with buildings at the top. And now it is going into railways as well. So general design philosophy has been, you can say, based on strength that we assume for the reinforcement as well as for the soil that goes as input into the design. We check for stability uh, with factor of safety against the condition for failure. So that is one part, but also now with high performance structures, the serviceability becomes more and more important, you can say. The recent code that has been released by BIS, I believe it is 18591, that documents all the conditions, design philosophy, and serviceability requirements with RRFD approach. In this, there are load factors and there are resistance factors. So instead of using a one load, you can factor of safety, we kind of factor it out in different components. And as a designer, I don't need to worry about too many background behind all this technology, sorry, all this way of designing. But or you can say background of design is not really uh, that difficult, but you don't need to understand as a designer too much in the back. But of course, the step by step is design and what factors to take where, that has to be learned, and that is well documented in the code now. So I would encourage all of you to use those codes for any design you are doing for highways in a way. I believe it is generally required by contractual agreements also now in a way. And in the end, of course, the load, whatever you provide, whatever is applied there, or it is applicable there, depending on kind of highways or kind of terrain that you have, height of the wall, etc. resistance has to be more than that. There are different components of design. We check for external stability against sliding, some eccentricity that is possible, and bearing, and also internal stability against pull-out. Then we also check for fascia connections and tensile breakage of the reinforcement. That is part of, you can say, that is also part of, in a way, internal stability. But serviceability requirements are more functional based, where you are applying this GRS wall. What is the use of that? Depending on that, the serviceability requirements may change. Vertical settlement in foundations as well as fill. So fill deformation also for lateral. So these are few things we have to check, and those should be within the limits. And of course, deep-seated failure is not acceptable. So that has to be checked very carefully, as in any other structure. So there are serviceability limit states based on where and what you're looking at. So aesthetics point of view, face stability, the thickness of the fascia will provide or will impose some limits. Damage to fascia, joint, how much is acceptable kind of thing. Joints widening, what is feasible, what is not feasible. Maintenance free, how much maintenance you want. In a way, of course, the more restrictions you put any of them, the serviceability requirement will get more stringent. And on top of all this, of course, the functional of adjoining a support structure, that is another aspect that we have to worry about. So if my GRS wall is supporting certain structures and they have their limits, those get directly imposed on GRS wall with the geometric corrections. Generally, the design methods that we have for the GRS walls are conservative, with generally ultimate limit state design, but serviceability will become important with more applications coming in picture. So if I look into that, then we have two types of design aspects that we need to, or serviceability requirements that we have to worry about. One is under static or operational events, and second is, of course, the extreme events. So this depends on type of applications and also type of load and deformations expected. The end of construction tolerance limit state can be one criteria, then functional or operational limit state, another one. And in long term, 10 years down the road, what would be the creep in the reinforcement or other components, and how much deformation that will bring, that has to be checked as well. In functional requirements, there are dead loads and live loads, pavement structures, abutment seat for true abutments, especially, and building footing for supporting GRS wall supporting other structures, and vehicular loading that will go in terms of highway loading or rails. They are different. And within those, there can be different levels of loading depending on where you are making this. So, for example, in trains, regular trains with the 120 kilometer per hour speed or slightly high speed trains that are being now operated, for example, from Delhi to Meerut, that speed limit is actually 180 kilometer per hour. But general operation is 140 to 150 kilometer per hour, which of course requires much more stringent deformation limits. And for high-speed railway, that limit will become further stringent, you can say, because you need to control deformations in a big way. So other than that, some extreme events, how much damage you accept, that becomes part of the serviceability limit design. And operational limits, how much deformation can you accept, how much can be corrected. So maintenance aspects will be taken into account. So these are generally defined by the design philosophy of particular application. And if general guidelines are not there, it will be made part of the contract where you're making the structure. Okay. So type of deformations that we look at is lateral deformations at fascia, the maximum deformation, or even sometimes layout, and vertical settlements due to foundations, and at as well as at the top of the wall, and differential settlements that are possible between wall base and outside or along the length of the wall. Okay, some criteria that are available for highways that are listed here. So depending on what kind of wall you are making, that will also play a role in terms of its own stability point of view, the restrictions. So for example, if you are using full height panel, which is like precast panels of 4 to 6 meters height, if you're using them, and it's like full panel is installed at once. I will show you some pictures of that. That is much more rigid fascia, and reinforcement is similar in the back, but that rigid fascia becomes, you can say, it provides more support in terms of deformations being less, but at the same time, they have a stringent requirement in terms of differential settlement as well. So one vertical 500 horizontal is generally required for full height panel to be designed, and total settlement not more than 100 mm. If you are using discrete precast concrete panels with initial joints width of 20 mm and bearing pads L by H1, so these are, you can say, incremental panels that you may have seen in highways in general. That will require one vertical, 100 horizontal. So it's little relaxed from rigid walls, rigid fascia walls, and the total settlement can also be much more that is allowed, you can say. Precast concrete segmental blocks. So those are like blocks that you saw in the pictures when I was showing on the first slide. So that is one vertical, 200 horizontal. Steel wire grade mesh gabions, if you are using those as fascia, those are much more flexible. So you can play around a little bit more, you can allow more deformations. So hill slopes where it is difficult to control, you can say, too much of deformations or differential settlements, this can be a very good option to use for GRS walls. Total settlement is again limited to 300. Wrap around with geogrids, geocells, again flexible, very flexible. So you can use them for that purpose as well. The difference between gabions and geogrid wraparound or geocell based solutions is in longitudinal direction, they have better performance in terms of flexibility of structure. So even difficult terrains can have these kind of solutions better than anything else. But long stretches, you may like more, you can say, long kind of rigid, relatively rigid fascia, and that is why you see a lot of highways, approach roads for flyovers being made with precast concrete segmental blocks or with panels. So this is total settlement 100 to 300 or 500 that I mentioned, but there is something related after construction. So once construction is over, how much settlement can you allow over the period of time? So in most of these technologies for highways, we can allow up to 100 mm even. The creep strain has to remain below 1%. That is generally the criteria that we follow, and that will be related with the settlement that you will see after construction. So there is a play between pre-construction deformations and post-construction settlements. So if you construct very fast, the foundations are not going to settle completely. And another aspect is the fill itself may be settling down a little bit if you are somehow not using select fills or you're using slopes, reinforced slopes in that case. So we have to allow enough deformations either, and that will reduce post-construction settlements. Or, I mean, you can imagine that whatever settlement could not complete within pre-construction uh, period or during construction period, that will get into the post-construction settlements. And those are like permanent deformations for the top functional requirements as well. If we allow that deformation to occur to the maximum possible, then post-construction settlements will be controlled better. So the serviceability criteria for highways through abutments. So generally, we say intrinsic settlements of 0.5% of structure height due to the deck load, post-construction of fill, that can be permitted. The settlement of underlying foundation soils, we assess separately, and that should remain within 100 mm after construction. Lateral displacement, 1% of structure height due to the bridge load. That is, you can say, generally used, but one can have more stringent requirements based on the confidence in the construction or design. Post-construction horizontal movement limit with respect to the creep, generally the strain is expected to be less than 0.5%. Now, getting into railways, we have more stringent, generally serviceability criteria. Depending on the speed of the train, it will become more and more stringent with higher speeds. And the deformations can be due to foundations, due to repeated loading, and due to fill compaction beyond the construction period that is happening with self-weight itself. So all these have to be accounted for. In repeated loading, you will have some dynamic component in the load. So load with the dynamic factor of the train, we account for that. And then that loading is applied for deformation assessments in long term. And that will also have creep effects of the reinforcements. So these all aspects are generally converted into very simple design criteria, which can be used similar to what you do in highways. But of course, there is a lot of background that goes into design before that, so that at the final stage of design steps, it becomes simple. With very high speed railways like 300, 350, 400 kilometer per hour speed, there are some wave propagations issues that come up, and they are also accounted for in the design. Different types of fascia wraparound I mentioned about. Timber fascia, some places are used, wired mesh, or you can say some kind of support in the front, which is made of wire mesh. Gabion fascia, reinforced extended at the interfaces generally. L-shaped block fascia, modular block fascia, brick fascia, then segmental panel fascia this is much more common in highways nowadays. But less common are full height precast panels and the cast in situ concrete fascia, but you will start seeing these also, especially in railways in near future. There are fascia classification with respect to that, how rigidity works. You have to look at only the last row in a way. So there are different types of rigidity that contributes to the overall rigidity of the system. And if I look at for the different fascia, how that works out is any of these wraparound block fascia, incremental panel, and supported incremental panels with double bars and bearing pads, they're low to moderate rigidity. And that means that the deformations after construction are going to be more in general. So below certain levels, deformation control is not possible with these kind of fascia. But the moment we go with rigid fascia like full height precast panels or cast in situ full height fascia, the overall rigidity of the system increases tremendously. So it becomes high to very high, and that provides you can say option for stringent serviceability requirements. The difference between full height precast panels, as you can see, it's a precast and installed on the site, so it needs big equipments. And cast in situ full height fascia, it is cast in situ, so it doesn't need big equipment. It can be there. But the another difference, of course, where the advantages are reversed, is full height precast panel is faster in construction, much faster, whereas cast in situ full height panel, full height fascia requires a lot of time for construction step by step in a staged manner. Uh, so fascia rigidity, of course, has very important role to play in terms of how deformations are going to happen over time. And other than that, of course, the stiffness, toe resistance, backfill stiffness, and creep effects in reinforcements, they are also important in the overall performance of the structure. But of course, how much support they provide, each one of them have their, you can say, role in overall design process, depending on what kind of a structure you're designing for. Decreased deformations and reinforcement forces, if you have more stiffness, stiff fascia, and it also transfers loads to the toe. So then how the toe is designed, that can provide some support, share some support, you can say. And a lot of innovation that can be done at toe level for that purpose. So in a way, you can imagine more like a hybrid design in terms of retaining structure versus reinforced soil wall with some rigidity in the fascia. Sharing of load among toe and reinforcement through fascia is the game in that whole process. And overall combination of these can give you much more high performance structures. So in the end, we are going to have focus on full height precast concrete panel fascia and full height cast in situ concrete fascia. Of course, I cannot get into more details, but I'll talk about briefly three technologies that can be used, that have been used rather. GRS structures, Japanese technology, that is based on cast in situ reinforcement, cast in situ fascia. So you can see some pictures of the reinforcement that are there. The walls that are there. On the left, you see walls, and on the right, you see the true abutments that are there, supporting exit from the tunnel near that, and where the road is crossing in between, something like that. The design here is stage-wise, and first you construct actually the fascia with wraparound, the reinforced fill with wraparound technology with support of wire mesh, you can say L-shaped steel support in the front, just for the local support, you can say. Then you see that is shown in the yellow, and then you see on the left, step by step, you're constructing the cast in situ fascia. Now, in between the process, the deformation in the fill is allowed to happen. It takes time, and that deformation takes care of, you can say, a lot of deformation that is expected in the foundation or the fill itself during the period when the fascia is being constructed. And sometimes we preload also this fill, so that you can say deformation is how much ever can be induced in the foundation and the fill. It is, you can say, taken care. So when your wall comes up and you can say the fascia comes up, that one aspect is it is integrated with the reinforcement. So you can say concrete gets into the reinforcement in that case, and that's why you need concrete resistant geogrids, either made from PVA, polyvinyl alcohol, or uh, Sometimes polypropylene can also help in that aspect. But generally, Japanese are using polyvinyl alcohol (PVA) for this purpose. So that interaction of concrete and geogrid, kind of integration of that, is on the inside, and outside it's exposed as finished surface. Uh, there are some supports that are needed to hold this the geogrid with the, you can say, sorry, fascia with the geo reinforced fill. So some anchors, etc., are used at some very you can say liberal spacing. So that way, that has a sacrificial role in the end, in a way. So the design is quite similar, but the sequence of construction allows deformations to occur during construction itself. And that means after construction, the deformations are going to be less relatively. So as I said, design is similar. So you have two-wedge model that you analyze for the internal stability, and you also check for fascia to be, you can say, deformation with respect to loading in the fascia by, you can say, solid structure interaction analysis. And other analysis, external stability, etc., you do as usual, that is expected in the end. If you look at this plot on the right, what you're looking at is deformation measurements for a structure that was made. 200 days is the construction period. So the most of the deformations, about 12 to 22 mm at different locations, two different locations, have occurred during construction itself. And after construction, it is in the range of about 2 mm, 3 mm, or 4 mm. In that range, you have deformations occurring. And you can imagine the structure is quite, you can say, quite high. The shape is shown on the right. And deformations of this kind, uh, you can say, can satisfy any stringent deformation requirements, even for high-speed railway, in a way. Uh, Another design from HSR, China, they also used another way of constructing, which is with slope, a little bit on the, you can say, outside, instead of taking it vertical, which is, you can say, combination of the Japanese technology we can use, or we can also use geogrids directly with polypropylene kind of material, or even other materials, polyurethane or something like that. Uh, Stiffer, the better. That is the whole idea. Uh, with slope, deformations during construction are there, of course, which are also reduced with slope compared to retaining walls, or you can say the vertical walls. Um, but also in long-term structure, it still remains flexible structure relatively. It performs better. But it has been used in China, but not many places otherwise. So Japanese generally used vertical structures. What you have to notice here at the right corner at the bottom is very stringent requirements that are applicable to HSR, and which is same for Japanese as well. Settlement less than 10 mm after construction, over 10 years, you can say. We did some finite element modeling and compare the results for our own research in some sense, and that kind of matched well. So that gave us confidence for model to work. We did some parametric study how you can say different aspects of stiffness contribute to overall performance, including the fascia rigidity and the reinforcement stiffness. And this information tells us that what is the range of the stiffnesses that we are looking at, beyond which we don't need to worry about it, you can say. So third design is precast panels. Long time back, they used to be very common, but over the time, it became more convenient to construct using incremental panel, and it was not necessary to use precast panels with big machines. And of course, flexible structures are always better. So that way, precast panels or block fascia are generally more preferred fascia in GRS structures, GRS constructions. Especially in highways, you will see all those kind of things, not full height panels. Uh, but wherever you have very stringent requirements, you can do so much with incremental panel or block fascia. Then you have to, with more and more stringent deformation requirements, you have to get into some kind of rigid fascia. Either the cast in situ, which is used by Japanese, that is one option, and with heavy machines, you can use you can say full height panel, precast concrete panels as well. They are generally installed first with support from the outside, the panels, and then in the back, you do construction by providing reinforcement at different levels and compacting the fill above that, as you would do otherwise in other rigid fascia structures. Uh, After construction, we should allow the deformations to occur before we get into functional functional aspects. And that way we can, you can say, uh, use up all the deformation possibilities in the structure before we get into constructing its top layer for functional aspects, leveling of for functional aspects. So these are some pictures of how the fascia is supported during construction, and then we design for different functional aspects. As I mentioned, that fascia rigidity and toe have, you can say, both have role to play in the rigid, these kind of walls. So the fascia being rigid, the toe is up to us. Uh, it can be freely frictional, you can say base, free base or frictional base, or it can be even restricted base. But of course, the moment you restrict the toe, the bending moments will increase in the wall. If that is acceptable, then you can use that to reduce the deformations in the structure, uh, controlling the deformations in the structure. And how that impacts, we did some studies on that, both experimental as well as numerical, and that contribution of toe can be significant sometimes, and it can help in design control. So there are different types of token conditions that we can look into, and not very difficult to construct, very easy, similar to what you do with leveling pads, but slightly more, you can say, jacketing, etc., that is possible with some deformation control. Some deformations we allow permanently in that, and some deformations can be elastic sometimes. So elastic means bending in the wall. So when the operational loads are removed, that the elastic load may be recovered, whereas permanent deformations will occur during the construction as well as after construction during the post construction due to creep effects, etc. Some deformations will keep occurring. So how their contributions are, we looked into those aspects with different toe conditions and role of toe, how that affects the response in both these aspects. So this combined fascia stiffness and toe conditions, elastic part and total rigid body motion with, you can say, permanent deformations. So all these studies are available, published. So we are not getting into more details here, but I'll be happy to discuss more later. So overall, the message here is that we understand now how with different toe conditions, bending moment, contribution or profile changes, and how we can take advantage of that, you can say, while the capacity of the bending moment resistance is available in the fascia. So that is the whole game. So I'll conclude by saying that there are so many alternatives with more functional requirements, whether it is water front structures or high-speed railways. The designs are going to vary. With high-speed railways, the stringent deformations required For that purpose, have you can say we have to think in a very different way with the new materials and new fascia designs. Uh, with traditional thinking of this works, that doesn't work, we have to depart from that and get into some new design systems. And they have their own, you can say, uh, nitty-gritties or smaller aspects to be learned from. And once I think we have some more experience with this, and of course, this Ahmedabad, Mumbai uh, high-speed railway construction, the bullet train project, there are many structures that are being made based on the first technology that I talked about, precast stage construction. So that is Japanese technology, and that will give us experience as well as confidence to build many more in future, not only for the high-speed railway, but other many applications that are there where you have stringent serviceability requirements. So this experience, along with some experimentation that we would hopefully do in next few years, we will see a much more uh, innovative designs coming up in near future. So with that, exciting times ahead. All the best for you, and I'll be happy to take any questions.
Thank you, Dr. Prashant, for the wonderful presentation. And so I think we can have a couple of questions since the session that you delivered is the concluding session for today. So we'll have a round of Q&A. So let me check, sir. I hope we shall start with
Yeah,
the Q&A.
yeah. Please.
Okay. So first question that we have is from Mr. Amit, and question says, Sir, GRS wall performs same function like retaining wall or RCC structure, shear wall, at basement in building. If yes, then what is the thickness and modulus of elasticity?
So let's not confuse with shear wall. It's a retaining wall, right? Shear wall has different purpose, and we should be careful there when we talk about that. With stiffness, retaining wall, uh, you can say whatever GRS walls generally being made, they are either block fascia or the incremental panel fascia. The stiffness required there is to support local soil over the width of the or length of the panel or block. Or you can say over the reinforcement spacing, right? And more than stiffness, the thickness of those components are guided by how much deformation you allow laterally. So whatever deformations you allow, it has to be at least 2.5 to 3 times of that, so that deformations do not cause those blocks or panels to kind of disengage. The design should accommodate that deformation. So that is the incremental panel and block fascia. With rigid fascia, uh, we can use them as retaining wall, but then it has to be designed on case-to-case basis, how much axial load you want to impose on them. Generally, they're still designed to be free at the top, and except some small loads of lamppost, etc., those kind of things, but more designed for the reinforcement forces being pulling on them on the rigid panels. I hope that answers the question.
Thank you, sir. So another question that we have, and question is from Mr. Ravi Sharma. Sorry, question is from Mr. Kanhere. Question is, how are the steel plates reinforcement protected from corrosion?
We provide extra thickness, so we have, you can say, estimate of how much deformations, how much corrosion can happen over what period, and depending on the design, you can say period, we provide extra thickness of the reinforcement.
Okay, thank you, sir. Another question. Question is from Mr. Avik Mandal. Question says, What are the various type of geotechnical instrumentation should be adopted for monitoring the behavior of full height panel RS wall, especially in case of use of retaining in high speed railway embankment?
Uh, I think we will be hopefully installing this instrumentation, and you will be able to see in a couple of years. That includes very comprehensive, actually, as well as with performance-based instrumentation. There are two types of instrumentations. Uh, you can say to understand the system, you have to have strain gauges in the back, in the reinforcements, as well as settlements measured at different heights, as and deformations, lateral deformations on the fascia. So that way, you can say all three components have to be measured in a very, you can say, dense manner. You can say, so reinforcement every second layer, third layer, or fourth layer, the tensile forces or or deformations have to be, displacements have to be measured in that aspect. And similarly, vertical settlements at some interval and you can say vertically at the foundation level as well as in between different levels. And on the fascia, from the side, outside, we measure the lateral movement that is happening. That is for comprehensive. But as performance you want to look at, you can measure simply the vertical deformations at the top, at least one location, and one lateral deformation at the top, something like that, whatever is feasible. Any of these will indicate any distress that is happening with time. So these are
Great.
mainly for information, but if any damage happens, you have to worry about that and fix it. That is independent of whether you did instrumentation or not.
Okay, thank you. So let us take the final question for today. Question is from Mr. Adil Bhatt. Question says, can we use GRS systems in flyover?
It is being used, right? So uh, most of the flyovers today, if you look at, have these vertical wall kind of things uh, on both sides of the middle part where you have concrete structure like a bridge. So that is all GRS structures. So I think in last 25, 30 years, most of the structures, flyovers are using GRS structures on the side. So probably you are asking question on the true abutment side. So can I support my deck also, which is at the top of the bridge or flyover on the GRS wall itself? That is the true abutment design, you can say. And actually it performs better than the rigid structures that we use otherwise in retaining abutments kind of thing. Yeah. So it is being
Okay.
used.
Thank you, Dr. Amit Prashant. I think it was a wonderful session that we had and a quite energetic one also. So now we are moving to close the first day of the Reinforce 2025. And now, as you know, that we are at the end of day one, I would like to thank on behalf of organizing committee to all our speakers, sponsors, and participants for joining on day one. And again, to mention that tomorrow we have day two of the session, and we are having exciting and deep knowledge presentation lined up for tomorrow's also. And so, on this note, I would like to thank you all again, and we hope that you all found this today all the sessions very informative and useful as it was for us. And also to note that tomorrow in the second half around 2:30 we'll be having a quiz, which will be a smart quiz, and it will be of 20 minutes. And everybody are invited and requested to attend that quiz. And towards the end of the day two, we'll be announcing top three winners for that quiz. So now we look forward to welcome you again tomorrow at 10 a.m. So our first session for tomorrow will start exactly at 10:30, which will be delivered by Dr. Madhvi Lataji. So we until then, stay safe. See you then. Thank you. Thank you all.